Hi, everyone. Hello there. My name is Myles. I work at a company called Famous Industries, heading up the famous.org project. Believe it or not, but I actually got into programming through music and art. This is an example of one of my installations that I did in my undergrad. It was called String Theory. It involved CNC milling a bunch of wood, a whole bunch of string, a lot of string, some lasers, some water, some cold-rolled steel. I have some scars from learning to weld. It was a great project, and it involved internally a bit of code with an Arduino, a bit of like hacking with the DMX protocol. And it was just like, I actually found art was a really great way to learn about code and learn about systems and how to build these large things. Another project that I did was the speaker bot. This is a really quick demo, so I'll just let it play out. So the speaker bot had an embedded Linux system and a Wi-Fi router in it, and then there was a Kinect hidden in the wall. And so using skeleton tracking, I was able to essentially make like a little theremin type device. Another project that I did was the Voxel Meter. This is a fun project using voxels to represent sound. And so what we're going to be talking about today is a little bit of kind of what you're seeing visualized here. What does that mean? What is sampling? How does audio get represented digitally on a system? So actually, I should probably pause that. Great. So all of this started with a device called a monome. It's a grid of buttons. It does absolutely nothing unless you program it to do things. And through that, I learned a programming language called MaxMSP. It's a visually based programming language, node-based programming. It's really fantastic. If you're an artist or you know someone who's an artist or wants to learn about sound or music or GL, it's a really great platform for learning this. It also allows access to the entire internal API through JavaScript. And this is one of the ways in which I originally got into JavaScript, was actually scripting in MaxMSP for making installation art. It also, if any of you are music producers and use Ableton, you can use Max to control all of Ableton and all of its inner workings. And this is just an example of, like how hairy a patch can get. It's a really kind of crazy way of programming. And if you thought, closures shifting right was bad, just look at some crazy Max code. But so my love of music and technology brought me to California to study at CARMA, the Center for Computer Research in Music and Acoustics. While at CARMA, I had an opportunity to learn about sound, the math behind it, physics behind it, how we compute it, electrical engineering, and most interestingly, like how our brains interpret sound. So this brings us to the topic that we're going to be looking at today, which is what is sampling. And so many of you might think that I'm talking about sampling like in the classic MPC sense of sampling blocks of sound, but that's not what we're actually talking about today. It's technically correct, but we're going to go a little deeper. We're going to talk about sampling sound in the sense of sampling individual chunks of sound so that we can represent it digitally. So a definition of sampling is a method of converting data, converting an analog signal to digital data which can eventually be turned back into an analog signal. So while we can sample many things, today we're going to specifically talk about sampling sound. So you can also sample any sort of signal, and a signal could be like a potentiometer or a button or a Twitter feed could be considered a signal. I mean, if you get into really deep in sample theory, like everything is a signal and everything can be sampled. But we sample sound every single time we make a digital recording. And unlike analog recording, which happens in constant time, a digital recording needs to be represented in sampled blocks. You can kind of think of a sample as a pixel for sound. So I'm going to give you all a bit of a primer on some sound terms that we're going to use to make sure that you're all on the same page as me as we're getting started. Sample rate. You're going to hear this a lot. And the sample rate is the number of samples used to represent a second of sound. And a common sample rate is 44.1 thousand samples. And we're going to get into that and why that is that number in a bit. Bit depth. And the bit depth is the number of bits that's used per sample to encode the data. A common bit depth is 16 bits. Codec. A codec is an algorithm used to encode a signal into digital data. A very common codec that we use is MP3. So let's tie all of those things together and kind of like figure out how this works. And we'll start by talking about a CD. So a CD is encoded using PCM at 16 bits per sample at 44,100 samples per second. The algorithm is called PCM, and it involves basically taking each channel and encoding it as a floating point number between -1 and 1. This is a floating point way of representing it. There's integer algorithms as well, but this is just like the simplest to grok, so we're just going to talk about that. And you can actually think about PCM encoding as an array, and each channel gets interleaved. So we can think about the array of samples that are on a CD as the first sample of the left channel, then the first sample of the right channel, all the way to like n number of samples that you have in your recording. And so this will be referred to as a lossless form of encoding. I mean, it's not entirely lossless. When you sample and unsample, like, that does disrupt the signal. But as far as encoding methods are concerned, PCM is considered lossless. A form of lossy encoding would be MP3. MP3 actually uses a variety of heuristics based on psychoacoustics to essentially say, hey, we don't need all these bits, and throw them out, and then like it's actually lossy. So there are limitations to sampling, though, and those limitations are part of the reason why we have these random numbers like 44,100. So this makes sense to everyone, right? No? Okay. That's called the Nyquist limit. It's named after Harold Nyquist. His work was built upon by Claude Shannon, creating what we know today as the fields of sampling and information theory. Yeah. The Nyquist limit really simply states that the rate in which you sample a system will dictate the maximum frequency that can be represented in that system. So at 44,100, we can only represent samples and frequencies up to 22,050 hertz, which sounds like kind of a random number. And anything higher than that actually gets aliased around back to the beginning. And we'll come back to that again, and that's kind of like a meta thing. But so 44.1 kilohertz, not gigawatts. It's the standard sampling rate used in audio. But why? It's actually the human ear is the reason. So the human ear only hears frequencies up to and around 20,000 hertz. So because of that, we can know, and it's just a basic heuristic, well, there's no need to encode any more samples. We could take 44,100 samples, we can represent signals up to 20,000 hertz, and pretty much everything that was in the signal that a human would hear would be represented. It's an optimization for compression. It minimizes the data that we need about the samples. So you may ask, why would we sample higher? So some recording studios will actually record at 96 kilohertz. This partially allows you to avoid aliasing, and 96 kilohertz, I have a diagram here to show it, gives you a lot more headroom. So you'll have what's known as like supersonic noise that will end up in a signal. So if you're doing like live recording in a studio, one thing you may want to do is actually like record your drums at 96K, do a filter of those top samples, and then sample down to 44.1 so you don't end up having those high frequencies aliasing and creating noise. Now, when you just have one signal, it doesn't really make a big difference. But as you start combining 5, 10, 15 different signals, all that noise starts adding up, and you start having a recording that doesn't sound very professional. So what does a lower sample rate sound like? That's a really interesting question. A telephone. A telephone actually samples things at 8,000 hertz. And I've got a really great live demo to show us. So here is an example of a recording of a voicemail message sampled at 44.1.
Believe it or not, George isn't at home. Please leave a message at the beep. I must be out, or I'd pick up the phone. Where could I be? Believe it or not, I'm not home.
So if we were to resample that at 8,000 hertz, we're going to notice it actually sounds exactly the way we would expect it to sound on a telephone.
Believe it or not, George isn't at home. Please leave a message at the beep. I must be out, or I'd pick up the phone. Where could I be? Believe it or not, I'm not home.
And that's actually not random that a phone is sampled at 8,000 hertz. The human voice, most of what is part of the human voice that the ear recognizes sits around, like 3,000 to 4,000 hertz. So there's no real reason to encode all that extra information. And by only encoding at 8,000 hertz, we can send a whole bunch more data over the wire. So let's go back to the human ear, and let's get into some really cool stuff and talk about why music works. So the human ear inside the cochlea actually has an exponential response. So you have all these little hairs. So if we go and look at that diagram, starting at the center, the hairs kind of go out, and they react to frequencies in an exponential pattern. So as it goes out, the response rate, I'm just describing something by saying what I said. That doesn't really help. So I'll actually show some diagrams. So an example would be A4. The note A4 is 440 hertz. The note A5 is 880 hertz. This is really crazy when you think about it, because as we actually experience sound exponentially, we experience pitch linearly. So there's actually this tie between an empirical fact and kind of an emotional response. As frequency grows exponentially, we experience pitch linearly. Boom. That is so cool. And all of music is built on top of this idea. It was actually originally discovered by Pythagoras, as far as I know. And he discovered a lot of what we now have created and know as the Western musical canon. The chromatic scale, Pythagoras. The diatonic scale, Pythagoras. The circle of fifths, Pythagoras. The greatest musical achievement in the modern era, well, that was actually Phish's Set 2 rotation jam during Deer Creek, Sunday, August 10th, 1997. But yeah, they couldn't have done that if it wasn't for Pythagoras. Musical notes, as we know them, have existed longer as a means of communication than the English language. That's crazy. That gets me so excited. It's the idea that if you're playing guitar and you're playing in a key that's positive, that's been communication between people longer than the English language. Now I know I'm probably wrapping up way quickly here. Wow, it's been 13 minutes. I'm supposed to have 30. But I think that's all that I have right now on paper. But that does give us time, I think, for a couple questions about music and sound, if anyone has any. But that's all that I have for right now. Thank you all. Cool. Oh, yes. Mm-hmm. I can do a live demo.
So you mentioned Max MSP as a really great environment for artists to look into music. And I was wondering what kind of capabilities you had in that.
Yeah, totally. I'll just do a quick live demo because we've got a bit of time. So let's take a look. So this is Max. We can go and we can start a new project. And we can start by just making a cycle at 440 hertz. And we'll connect that to the output. And we got some sound going. So what we can do that's really interesting too is anytime you're actually changing the amplitude is just multiplying. So we can take the output of this and put it into a multiplier here. We can connect it, and then we can make another cycle that's running at 10 hertz. We can connect that and multiply by it, and now we're going to get amplitude modulation. And then we can take, another one of these, and we can do frequency modulation as well. So we take another cycle, we'll put it through a number object to turn that signal into an actual number. And then what do we want to do? We want to take it, we want to add 1 to it so that it's not zero-based anymore. And then we can multiply it by 220. start kind of like changing that. We could like literally just copy this whole thing. We can encapsulate it. We could duplicate it. Add another one. Hop in this one. Change this one to be like. That's music, I guess. So this is the monom that I was talking before, and just let me know when we need to stop, because I'll just keep going. So I built this one a couple years ago. I think I can just kind of like, yeah. So the case comes out, and there's like electronics in there. It's really pretty. And so the case, the top part is steel milled aluminum, and then this was like hand routed. It actually was another monom's case, and then I got it secondhand through a form. You could tell the edges where I roughly routed it to shove this case in so that it all fit. So we plug this in. It's gonna give a light. And so there's some fun things that we can do like really quickly with this. So we can open up monom serial, which is this communicates to the computer through serial. Monom serial picks up the serial communication and then converts that into OSC, which is Open Sound Control. It's an alternative to MIDI. It's really nice because it does everything over UDP, so you can do a lot more than you can with MIDI. MIDI, you really only have like 128 messages. OSC is kind of like infinite. So here's an example of a patch for a spectrometer. So we can go and grab my voice, and then we can just see like really quickly that, and this is like totally building on everything that we were talking about earlier too. We're taking a sample of my voice, we're putting it through a Fourier transform, and so a Fourier transform, what it's going to do is it's going to take the sound that's currently being represented in the time domain, it's going to put it through a transform and represent it in the frequency domain. So each one of these bins is actually representing a chunk of frequencies. And then over time, we're able to basically say, hey, you know, like I just care about the granularity of an 8x8 grid. And so we can kind of like take a look at max programming a little bit here. If we dig in, this patch was written by Brian Crabtree, who's online known as Ten, T-E-H-N. He's the creator of the monom. He's a really cool guy. But this is basically what's going on under the hood, which, you know, makes a ton of sense. But I mean, like, there's other fun things that we could do too. So, like, in Ableton, for example, let's see if this works. I can go to my Max for Live folder. I have this one thing I really love using called Raptor. So we throw a Raptor in here. Oh, wait, that's not Raptor. That's Raptors. So there's Raptor. And I connect Raptor to the monom, and now it shouldn't be, yep, that's exactly what I'm expecting. And we can go and grab, like, there's this synth I really love called Boards, and it's like a Boards of Canada ripoff instrument. Everything sounds good. Like, you don't even need to, like, think. It's just like, you throw this in. I'm gonna, like, make up, like, a hit right now. It's amazing. So Raptor, like, I'm not a huge fan of C, so let's go into G, and we'll set up this loop group to be 4 bars. So we can kind of start. So we can kind of just like let that go and just duplicate it and then just like put in another synth that someone made that I don't have to think about. Like we'll just do something that has the word bass in it. That's not bassy. Oh, you know what's actually really great for not having to think about it? I really love not thinking about things. The instrument rack in here has these like evolving synths that are really awesome. Yeah, these rhythmic ones. No, the ambient and evolving. Yeah, something like that. This is gonna be music. What's awesome is that like everything in here is beat tracks, so I can just go and like go into my tracks folder and grab some acapellas and just throw them on top and it'll just work.
It's the one and only Digo Double G.
Snoop Dogg. Snoop Dogg.
Da 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 da. You know I'm mobbing with the D.O.E.
Yeah, yeah, yeah. You know the West Coast is back for all you suckers. Suckers. So put something in the air. Put it in the air.
Top dog, bite them all, yeah, I'm burning it up. D.E.G.C. You should be turning it up. C.B.T. L.B.C. Yeah, we cooking back up. And when they bang this in the club, baby, you got to get up. Cause homies, thug homies, yeah, they giving it up. Low life, yo life, boy, we living it. The one and only da 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 da.
So something like that you can do really easily. Are there any other questions? All right, cool. I'll call it now. Thank you so much.
That was amazing, Myles. Thank you.